sample that reaches a target, and whenever we actually try to trigger the bug or whatever, we can't reach it. So we would like to have a description of all possible input sets that lead to a certain location. The first idea how to do this is, or the more or less, the obvious idea to do this would be using genetic algorithms, because you have a very, very clear fitness function. You can measure the distance in basic blocks from your target to your current execution on each input. So given such a good fitness function, one would think that genetic algorithms might be the solution. There's a talk today by Cunningham, Embleton, and Sparks, which is going to use that on it's called Sidewinder, something like that. So that's going to be interesting to see. I personally am not quite sure whether this will work for complex cases, but we shall see. Now, the second idea is a little bit crazier. The second idea implies that you model a path through the executable as an equation system mixing modular arithmetic and Boolean functions like XOR, AND, OR, NOT, and ROR. And you can thus, if you can model the path, and you can model the path in almost all cases that way, you can turn the problem of reaching that certain location into a satisfiability problem. I'm not sure, like, if you've ever had any lecture on theoretical computer science, they drill this thing into you, which is called 3SAT, and how it's NP hard, which is given a large Boolean formula of a certain form. It's NP hard to see whether it's satisfiable. And this is essentially just a satisfiability problem, where you get a large Boolean formula with all the input bits as variables, and then you'll try to solve it. Second possibility would be to regard the entire thing, like you can transfer Boolean formulas into polynomials over F2. F2 is the values of 0 and 1. So you can just transform that into polynomials and perhaps attempt to solve these polynomials. For actually doing this, there's public SAT solvers, which are actually quite good at certain problems. Like while in fact the problem is NP hard for some problems, in practice, a lot of relatively complex SAT problems can be solved even when they have several 100,000 variables. So there's public SAT solvers, or there's OBDD-based algorithms. OBDDs are a special data structure used for representing Boolean functions, meaning functions mapping from a bit string to 0 and 1. And they can be used for representing very large sets of data, meaning if you have you can have 20,000 different values that all satisfy one given OBDD. An OBDD is basically a special form of well, you know, you can, if you have a set of Boolean vectors and you want to represent that set, you can describe that as like an if-then-else relation, basically. If the first bit is set, then do this. If the second bit is set, then do that. And OBDDs are basically a huge decision tree collapsed into a relatively compact graph, which means it can represent very, very large sets of Boolean vectors in a very, very compact manner. All right. We've been doing a little bit of that stuff at home at Sabre, and my guess for difficulty is that if you have no multiplication with two non-constants involved, or basically no multiplication with, multiplication is generally a bitch, and it's not so bad if one of the factors is a small power of 2. And if you don't have multiplication and you really just have add, XOR, roll, if you only have add and Boolean functions, it's relatively, or it's pretty easy. If you have rotations, it can get a little bit harder. And if you have multiplications, it's, I don't know whether it's possible. Now, complicating this entire thing is that having input to exercise a certain path isn't enough, because most paths will depend on application state. So this is the real big complication. We'll have another challenge regarding this later on. Determine which functions to execute to get the application into a certain state. Well, of course, this won't be possible in the general case, but let's say we have something like a network daemon that has a state variable which can have values 0, 1, 2, 4, 5. It should be possible to identify the functions in which these state variables are updated, and then try to, okay, I need state 2 to exercise this path, so I first need to run down this path to set the state accordingly, come back and then run down the other path. Generally, I think challenge 5 is one of the most difficult problems I can possibly imagine. One of the most fun ones as well, but those two things tend to go together. Challenge number 6. Everybody and his dog is writing VM, like translation and VM-based protections these days. And it's getting slightly boring. Somebody, like, it started out in 96 or 95 with Soda Designer writing these things. And then it was done in a few commercial copy protections in 2000 or up to 2000, 2001. And now it's everywhere. And everybody who thinks it's cool writes like a translator and emulator. And it's getting boring. And we need methods to automatically analyze PE cryptos that take an application, translate it into intermediate language, and then start emulating it. Yeah, and well, I don't really know how that would work, but from my experience, the standard architecture for such a VM-based protection is that you have a VM, and that VM has a context, meaning like the set of registers of that CPU, some sort of data structure. And then it has a decoding loop, where it fetches a new instruction, and then uses that instruction to branch off to the different instruction handlers, and then they update the context somehow, and then it returns. So a trivial and easy thing to do would be just generate a generic debugging framework that you, each time you see a VM-based protection, just hook into this decoding loop, and that lets you see the changes to the virtual CPU context on every iteration. That's basically just one breakpoint at the right spot in the loop and knowledge of the data layout of the context. All right. Then the difficult part, attempting to automatically recover semantics of the individual instructions. Which means if you have a handler branching off to what is like an addition for the virtual CPU, try to determine automatically that this is an addition. Of course, this can be made arbitrarily hard by the guy writing the VM, but in most cases, I think it will be relatively easy. You'll just see, okay, we're sending these registers in, and now one register contains the value of two registers summed together. I don't know. Thing is, yeah, I really have no clue how hard this entire thing is. I just know that we need infrastructure to build, like to work with these things, because I'm tired of people thinking they're really cool. All right. Challenge number 7, normal form for code, another difficult one. A lot of the polymorphic engines we see these days are basically just glorified table lookups. So what I do is I have a bunch of instructions, and then I take a block of code, and for each instruction, I look up in the table and choose one of a set of possible semantically equivalent representations for that instruction. Meaning I just expand like an add EAX20 to a bit of ugly code like on the right top or on the right bottom, and then you just iterate this. And you can make code arbitrarily ugly by just taking code, throwing it into the morpher, and then throwing it into the morpher again, and throwing it into the morpher again, and your code will just balloon, and the signal-to-noise ratio for the person taking it apart will go crazy. So what we would really like to have is, well, under the assumption, well, in general, of course, this is not possible, what I want, but let's say that the translator is not allowed to add memory access, and the translator is not allowed to do self-modifying code. So any substitution which we do here has to just substitute one instruction with a set of others that don't access memory and that don't self-modify. Under that assumption, can we build a reduction that takes a bunch of code and reduces it to a common normal form? Meaning that if I have two code sequences S and S dash, which were both derived from the same source, then I run my reduction relation from them, and I get not necessarily the source, but I get the same normal form in the end. Because if you can do that, you can just strike down 85–90% of all the polymorphic engines that I've seen. Because, well, you just take one sort of polymorphic thingy, and then you reduce it, and you take the other polymorphic thingy, and you reduce it, and then you can compare the results. All right. I'm not sure whether this is possible. It sounds like a really fun project, though, and for those of you who are a little bit more theoretically inclined, that might be something to spend a bit of time on. All right. Challenge number 8. This might actually be relatively easy. Visualizing call graphs is quite important for understanding programs. So we have a graph with like a function, and then all the functions that are called from this particular function. And the disadvantage of this view is while we see that this function here calls these other functions, we lose all concept of ordering. And implicitly in the function calls to subfunctions are ordered. meaning it makes a great difference whether I call string length malloc memcopy, or whether I call memcopy malloc string length. Like there's just, from the semantics, like trying to understand, why are we generating the call graphs in the first place? We want to understand the program. So when we want to understand the program, we want to recover semantics by just looking at what functions it's calling. And within each function, the subfunction calls are ordered, and we lose all that by our current representation in the call graph. And the question is, can we find a visualization mode that keeps us and visualizes for us the concept of the order of the subfunction calls within a function? I don't know. I think it should be relatively easy, but I don't know. 10 minutes, cool. Challenge number 9. Given an executable that is a network daemon that does some sort of protocol parsing, attempt to construct a state diagram telling us which functions can be reached, like, okay, under the assumption that we can identify the state variable, which is going to be an integer of some sort. Can we generate a diagram telling us which functions are reachable in which protocol state, which functions can be used to move the protocol state to another state? Essentially trying to generate a form, like a sort of diagram from the executable telling us, now we have this CPU protocol state, and from this protocol state we can move to that protocol state by use of this function, and to that protocol state by use of that function, and we can't go from this state to the other states. Okay, because when it comes down to us no longer having overflows, we'll have to do a lot of protocol analysis, that's for sure. And protocol analysis, well, I end up drawing these sort of diagrams on paper anyhow when I try to do these sort of things. So might as well try to do this automatically. Yeah. I don't really know how hard this is going to be. I think it is going to be terrifically hard in most of the cases. But if it works in about 40% of the network daemons, or just in special cases, like if it can save me a week of work on 2 or 3 daemons I've been working on, or it's more than a week of work, if it can save me a month of work on a few daemons that I've been working on, then it should be worth it. All right. Challenge number 10, semantics-based library signatures. Would be nice to be able to recognize a string copy even if it doesn't have the same byte signature as a string copy. It would be nice to recognize a string copy if the programmer has decided to hand roll it. Which means I would like to have semantics-based library signatures. And something like, I want to automatically be able to recover stuff like, this function here does an insert into a linked list. And I don't know how to do this, but one of the ideas would be to view a function as, like, memory is an abstract graph, and try to view a function as an operation on this graph, modifying this graph somehow. And then see whether we can match functions based on this modification of the memory graph. I have really no clue how good this would work. And I think for many functions you just wouldn't be able to do it. But if we can do it for hand-rolled string copies, then that's already very, very valuable. And if we can do it for stuff like insertions or removals from linked lists and so forth, that's damn useful. All right. Number 11, something that's not really serious yet. Once we have all these things, build a static analyzer, string it together with an input crafter, and then try automated exploitation once you trigger the bug. That won't happen. I don't know. If it happens, it's going to be amusing. But yeah, let's just skip this slide. All right, I'm nearing the end of my talk. There's a few other things that I would like to say. In order to work on these things, we, as the reverse engineering community,